So we'd like to discuss somebody new, what we did last week, which is kind of important. And if you don't go, I'll breathe on you.
So we mainly discussed partial and semi-partial correlations.
It's important to know what those things are, so you can, since you're leading the discussion, you can ask your colleagues what those things are.
So the general concept is that you want to take out residuals so that you can identify how something impacts your outcome variable uniquely. Anybody else want to add to that?
Is it with the partial that you take out residuals for both variables and then semi-partial you do it for one?
Right. Right. So in partial, we residualize both the independent and dependent variables. For the semi-partial, we only remove variance from the predictors, right? And that's essentially what multiple regression is. And when we get into the multiple regression, I'll show you how we can translate these things back and forth between each other, and come up with what are called beta coefficients as well, which you already know what they are. You just we've dealt with them in multiple variable regression so far. Okay, all right. So there's a couple of things here. Let's start talking about what are some uses you may have seen in the literature that you guys have read for multiple regression. So how have you seen multiple regression used? Because it can be used for lots of different things.
So like the frac score for calculating when you need to treat someone. So if they developed a model where they used a lot of predictor variables and then pieced ones out that didn't add anything. So to get a very parsimonious model.
Good. All right, I like that. Good. So that's in some sense theory building. Okay, good. That's very important. Yeah. Build theories.
Prediction rules.
Prediction rules.
You're trying to isolate the effect of one, or the relationship between a variable and an outcome, and you want to control for all the other.
Good. So we want to see the relative importance of one variable or one set of variables compared to another variable or set of variables. Anything else? How about to test a hypothesis? We have a hypothesis that if this intervention has some incremental effect over some standard of care, we can test that hypothesis, right, in a regression model. We can use it that way too. So regression is a very flexible tool. It's an incredibly flexible tool. And how you use that depends on the quality of your inferences or vice versa, all right? So let's talk about some multiple regression strategies, all right? The one strategy we want to talk about is for prediction purposes, right? So one strategy we can use multiple regression for is that we can just throw every variable that we can think of into the regression model and come up and do what's called simultaneous regression. And in simultaneous regression, we don't do that stepwise thing that we referred to when we were partially and we were building that incremental R like we did with the semi-partial. In a simultaneous regression, all of the variables are put in there all at once. Okay? And as a matter of fact, with simultaneous regression, or when we're trying to build some prediction algorithm, we're not even necessarily interested in p-values or anything. We're not interested in interpreting the coefficients. We're simply trying to minimize the sums of squares between our observed and our predicted, right? So it's purely in some sense, a mechanistic exercise, right? It's a mechanistic exercise. So when we use regression for that purpose, we have to think about what happens when we apply the regression algorithm to a single set of data. It's entirely possible that, it's actually very likely, that our results won't generalize from one set to another data set to another data set to another data set. So what we have to do is come up with some sort of validation process when we use regression for prediction. And a reasonable strategy is something called a k-fold validation. K, just the letter K, stands for the number of ways that you're going to chop your data set up randomly. So generally we set K to be 5, right? So we'll take our data set, say we have 100 observations in the data set. What we will do is, let's see if I can draw this. So these don't stand for observations. These stand for a set of people in group 1, a set of people in group 3, and so on and so forth, right? So what we would do in this k-fold validation is we would run the model. The first model we would run it, but we would exclude the 5th group. And then we would see how well the model that we built based on the 4 groups predicts the outcomes of the 5th group. Then what we would do, we would run a second model, and we would exclude, say, the 1st group. And we would do 2 through 5 predicting 1, and so on and so forth. And we want to see how stable those predictor variables are.
So it's
Okay?
kind of like changing your, just your population
The sample.
and just running the
Yeah.
equation.
Yeah, and we want to see how stable those statistics become. Right?
Do you run it as many times as you have groups, so you exclude each group once, or you just?
Essentially, yeah. And then for each, if I have 4 groups then predicting a 5th group, so what I'll be able to do is based on my first 4 groups, I'll get some sort of R squared for those data. Do you think if I were to take that model that I built on these 4 groups and apply it to the 5th group, do you think the R squared would be higher, as high, or lower than the original data? That's a good question. Make sense?
Should be as high.
Okay, so the question is, I get an R squared from my model based on 4 groups, right? I'm then going to take that regression equation and apply it to the 5th group. So for the 5th group, I'm going to get an R squared for that model, right? Will that R squared, when I apply the regression model, be as good, worse, or better?
No, it should be much better.
It should be worse.
Worse.
I would expect it to be worse, right? Because if the R squared is going to be optimal here in the first 4 groups because it's based on the observed data. Now I'm applying that prediction algorithm outside the sample that I used to create it, right? So what will happen here is that the R squared will shrink, and we call that shrinkage.
So to generate these 5 groups in the beginning, are these just random?
Random. Randomly assigned one of 5 groups. Okay.
Sorry, so that's
yep.
called simultaneous regression?
Mm-hmm.
Okay.
So anytime you include all of the variables of interest all at once,
Mhm.
that's called simultaneous regression.
Including like the variable that you're.
The variable of interest.
Interest.
Yeah, so simultaneous means, let's say you have 10 candidate predictors.
Mhm.
You throw all 10 in all at once.
So you end up with 5 separate equations?
Yes.
And you choose the one that has the least amount?
You average them.
You average. why would the variance be lower, in the fifth group? And,
Oh.
And why does that mean that, and I thought that would mean that the prediction was better.
If the R squared is lower, that means I've explained less variance
Oh, okay.
than the original data, right? We would expect it to be lower because the data that we're using was not used in building the model. So we're generalizing from the observed data, and then we're going to apply that algorithm to a new set of data. And we would expect it to not do as well.
Okay.
Okay. So that being said, I'm not going to talk much about prediction because it's outside of the scope of what it is that we want to talk about in this class with respect to theory building and hypothesis testing. Okay? Okay. A second strategy is to simply use simultaneous regression. Right? So that strategy is, you're going through your data set. If you're using secondary data, and you're going through the list of variables, and you should be doing some sort of conceptualization of what's going on in the world, right? So from a clinical sense, when a patient presents, one of the first things you do is you do a case conceptualization. What gave rise to this? What should happen? If I do this, then this should happen, right? That's case conceptualization in 4 words. The same thing it's sort of the same thing that we do in science, because case conceptualization is in fact the scientific method that we observe, that we talked about in the first day of class. Patient presents, you observe. After your observation, you give some preliminary diagnosis. That's codification. After your diagnosis, you come up with some sort of treatment plan. That's a hypothesis. You apply the treatment plan to see if it works or not. That's testing your hypothesis. Right? So it's the same. It is in fact the same concept. So in simultaneous regression, it's the idea is as if you're going through your secondary data set, conceptualize your case. If I have some outcome of interest, before you even look at your variables, start thinking about what types of variables you believe are going to be related to that outcome. Right? That's a very important thing. The other thing you can start to think about are my predictors going to be related to each other as well? It's entirely possible that some sort of treatment could be correlated with another predictor. For example, there's a method called instrumental variables that's used a lot in medicine. And you think about it, in an emergency department situation, what's a really good predictor as to whether or not somebody goes to, let's see here. The accident, the trauma happened here. There's an emergency room here, and there's an emergency room here. What's a pretty good predictor as to which ED they're going to go to? The distance. Distance to the trauma center. So we would actually call that an instrumental variable. Let's say that this was not a trauma center. It was, I don't know, a run-of-the-mill emergency department. I don't know what that is, but I'm making it up. Right? But here's where you guys are, right? So you could think about, well, a predictor of survival might be quality of treatment, for example. Well, if I have a top-tiered trauma center here, and this is a run-of-the-mill ED department, then the idea that distance is then going to be related to the emergency department that they were then admitted to. Then we have a problem, because there's an assumption in multiple regression that states that our variables will not be correlated with each other. All right? So that there's a new assumption that we have to talk about. The assumption says that there is no multicollinearity. So again, if we were to draw multicollinearity, we get into this situation where all of the variables appear to be related to each other. Right? So if I were to just label these things, we see x1 and x2 are both related to each other graphically here, right? The extent to which these two things are related to each other, remember we had this region that this region C that we kept talking about, I don't know how to interpret. Actually, when you do the matrix algebra, which again I would never ask you to do, when you do the matrix algebra, sometimes this C area makes it so that you can't do the regression. Your regression actually blows up. The computer will go, it gives up, I don't know what to do. All right, Stata is a really interesting package in that if it runs into this multicollinearity problem, it's going to throw one of the variables out for you. The problem with letting the computer decide which variable it throws out is that it may throw out the wrong one, given your case conceptualization or your study conceptualization.
So how does it decide?
I don't know.
Okay.
It may do it randomly, right? I'd actually have to look at the manual just to figure out exactly how it does it. So this multicollinearity problem occurs when our predictors are very highly correlated with each other. So now I'm using an adjective. So how do we define highly correlated with each other? And oh, by the way, if I had, let's say that I had, x3 and x4 and all that stuff, right? Remember what I would do to get the, excuse me, this, I would regress x2 on x1, x3, and x4. It's just a generalization of what we did before, right? And we would come up with an r squared for that. If we have an r squared where the other predictors can predict, say, 80% or more of the variance in our outcome, then we have a problem. Then we have a multicollinearity problem. There's something called a variance inflation factor, which we'll learn about. A VIF, variance inflation factor. Luckily Stata does all of this stuff for you. And just to confuse you, there's also something called a tolerance statistic, which is nothing more than the inverse of the variance inflation factor, which you already understand what it is. So if I do 1 minus rxy squared, what's that? That's the coefficient of alienation, right? So the tolerance would be the amount of variability in x2 left over that variables x1, 3, and 4 don't predict in it. So if I have a very small tolerance, that would be bad. Conversely, if I have a very high variance inflation factor, that's bad because this is simply the inverse of this. And I'll show you what that means in a very concrete sense. Anyway, as a consequence of this collinearity issue, the algorithm doesn't know what to do with that area C in with the data, right? And if you recall, when we look at a regression table, we have the idea of a parameter, then we have like a t, and then we have the standard error, right? And then we get a p-value, right? So to get the, actually these will switch. So to get this t statistic, we're going to divide the standard error in the parameter to get the t statistic. What happens is when we have this collinearity issue, when the variables are highly correlated with each other, again, it doesn't know what to do with that variance. So you can think of it as a metronome. It's going all over the place. It's swinging wildly, trying to figure out who should get credit for that variance. As a result of the collinearity, the standard errors become wildly inflated. wildly inflated. They will be orders of magnitude greater than, say, the coefficient or any other standard error in the equation. So that's a good way to pick up as to whether or not you have a collinearity problem. And for those of you who've done matrix algebra, again, I'm not going to ask you to do it. This becomes a problem because it's inverting a matrix with a 1 on the off diagonal, which is impossible to do. You get numerically unstable results. And as a result of that, standard errors blow up. The funny thing, though, is with this variance inflation and the multicollinearity is that the parameter estimates will still be unbiased. So if you're using regression for prediction, you don't care if your variables are collinear, because you'll still get an unbiased prediction, an unbiased parameter. What will be biased is the standard error. Okay? Which leads to problems in interpreting simultaneous regression results in the face of these other issues. Okay? You with me so far? Yeah. You have that look on your face
Can you
again.
say again why the standard error gets bigger?
Because the algorithm doesn't know who to give credit to that overlap, to that variance to. So it sort of bounces all over the place. It says, I don't know, and gives up, and it inflates the standard error, which is why we call this a variance inflation factor.
And you mentioned that 80% kind of correlation between two variables
Becomes
is
a
high.
problem. Yeah.
Okay. Is that kind of like
The rule of thumb.
80% or
Yeah,
higher?
80 or higher. Some people claim 90. But I would say that, look, if you have a set of variables that predict 80% of the variance in another variable, that's pretty redundant. That's fairly redundant. Not correlated 80%, as an R squared of 80%, that's high. All right. So with these simultaneous regressions, we now have a model. We would have a model that looks like this. All right. So the interpretation of the coefficients don't change based on what we've learned on how to interpret these coefficients, both from the semi-partial correlations and when we did bivariate correlations. So the beta 0 is still the y-intercept, and that is the expected value of y, except not when x is 0, but when all of the x's are 0. Right? When all of the x's are 0. I interpret this beta 1 through beta k, I'm just using k as the number of predictors in my equation, as saying this is the expected change in y holding the other variables in the equation constant. Right, so that's why I started off talking about partial and semi-partial correlations, because it has a natural interpretation based moving into multiple regression. Okay. What we did before still holds. We're still going to define error the same way. This whole system now becomes the expected value, right? So what multiple regression is really trying to do with these beta weights here, with those regression weights, it's really trying to come up with what's called a linear combination. How do I optimally weight all of the variables in my equation in such a way that when I add them together, this new expected value
right? I'll come up with this, I can rewrite as y hat I, right? Maximally correlates with yi. So once we do all of this, it gets back to what you already know in bivariate correlation. So how do I weight these variables in such a way as to optimally maximize the relationship between the observed variable and the predicted variable? And the multiple r squared, which we've been writing down as capital Rxy, is really the correlation between yi and yi hat. That's what the multiple r squared is. It gets back to what you already know. Okay? So there are a couple of ways that we can do this. There's a couple of algorithms that we can use to estimate these betas. All right. One method, and these are estimation methods. So let's talk about those for a minute. We've been using ordinary least squares, OLS, as our estimation method. When we do our stuff by hand, we've been doing it the old-fashioned, what we refer to as a closed form solution. We can actually write down the mathematics to come up with the best answer that will maximize the relationship between y hat and y observed, right? So there's closed form solution that refers to ordinary least squares. You can actually write down the equation. With the advent of computers, high-speed computers, the ubiquity of high-speed computers, they have generalized the algorithm into something called maximum likelihood. And so perhaps you've heard maximum likelihood regression, something like that. No, has anybody heard of this? Okay, so think about it. You remember again, we're not going to do the calculus, but remember in calculus when you found the root of a number using Newton's method? You don't remember that? Where you guessed a low value, then you guessed a higher value, and you wound up eventually pinpointing a value where the root never changed very little? Okay, well here's how it works. I'm going to give you the non-technical explanation of maximum likelihood. Okay? So again, we're not going to do this, but I just want to give you a sense of what's going on. Let's say that I have three variables in my equation. I have this, I have 1, 2, and 3 variables. All right? Think of it as a dial. Each variable has a dial that I can either turn up or I can turn down. All right? So let's say my assumption, in my first go around in my iterative approaches is that I'm going to make the assumption that none of these variables are related to the outcome. So the first thing I'm going to do is I'm going to set these betas to 0. And then I'm going to get a fit for the model and see how well the data fit that model. And then what I'm going to do is one by one, I'm going to click this one up just a little bitty bit, leaving the other things constant. And I'm going to fit that model. And then I'm going to do the same thing for the second one, and I'm going to do the same thing for the third one, and I'll do 2 at a time. And then I'll do all 3 at a time. So it's fiddling around with knobs. You guys are too young to remember UHF, VHF, rabbit ears. Oh, good. This may be the last class I get to do this for. But remember that? You're like, oh, I'm so close, then you turn it too much, and you're like, damn it.
It's red.
Then you got to go back, right? Think of maximum likelihood as the same way. So you're fiddling around in space, trying to find the maximum position on the dial, the positions on the dial that will maximize that value. So there's no mathematics per se behind it. You're guessing. You're wonking around in space. I guess that's the easiest way I can describe maximum likelihood. Well, if you remember, for those of you who remember Newton's method of finding the root of an equation, you'll guess here, you'll guess here, you'll guess here, and eventually you keep bonking around in space until you find that tangent. If you know you found the tangent of that line when the number stopped changing. That's essentially what we're doing here, except I abstracted you away from the tangents. Okay, so but in the end, maximum likelihood estimates and these closed form ordinary least squares methods will come up with the same results, come up with the same estimates. So in Stata, if I want to do multiple regression, I can use the regress command, or there's another command in there called GLM. Regress uses the least square as estimating method, whereas GLM uses maximum likelihood. One advantage of learning GLM, the GLM command, is that the general linear model, bless you, the general linear model, which is what we've been talking about, then expands to something called the generalized linear model. And the generalized linear model includes things like logistic regression, multinomial regression, Poisson regression, negative binomial gamma, and all kinds of other regressions that you've probably heard of. And the interpretations of these coefficients mean the same thing.
What kind of questions will we be able to answer with GLM that we wouldn't be able to answer with regress?
With regress, you're stuck with a continuous outcome.
Okay.
Right? So let's talk about that for a second. An assumption that we're making, an explicit assumption that we make when we're doing least squares regression is that the variable of interest is continuous. It's continuous and theoretically can take negative values and can theoretically take on any positive value. Right? Whereas in a binary outcome, like dead or alive, male, female, Democrat, Republican, it's 0 or 1. So the space has changed. I can also think of count data, like how many times did you go to the emergency room? How many puffs did you need on your emergency inhaler in the past week? Those are count data. And the smallest count number would be 0. And I can't have a puff and a half in a day. I can have whole numbers. So that's a different model per se, different distribution per se, but I would still write down the model the same way. Except I'm going to make different assumptions about the distribution of my y and the different assumptions about the distributions of my error. But conceptually, they're the same thing. I'm going to interpret the beta coefficients exactly the same way. For every 1 unit change in x, I expect beta different changes in y. Which is why I spend a lot of time in the beginning talking about what it means to partial out and how to interpret these things. Because once you got the multiple regression, everything else is fairly straightforward and simple. Okay.
Are you saying you can't use ordinary least squares with binary?
You can, but if let's say that I had, I coded my data as 1 alive, 0 is dead. It's entirely possible that I could come up with a predicted value of, say, -0.04, which is out of the scope of my plausible values.
If you use ordinary least squares.
Yeah. And as a matter of fact, back in my day, before we had fancy dancy computers, you guys Dana Carvey fans? No? Okay. No? All right. Saturday Night Live, the church lady? Back in my day, he was the grumpy old man. Anyway. We actually used to do what are called linear probability models. So because we didn't have computers to do maximum likelihood, we used to use least squares to do logistic regression. And, you know, we had heinous outcomes in some cases.
So if you use the maximum likelihood,
You will restrict your results to be within your domain appropriate values. Okay.
So you have R, X, Y, the multiple
Yep, multiple
R squared.
correlation, yep.
So that's the value that's being maximized. Is it the correlation, is it all the variables, like X?
Yeah.
X1, X2, X3?
Yeah.
Okay.
So look at this here. So I'm adding these together. That's when we say general linear model, we say that the model is linear because we add things together. So what happens is I add these weighted variables together. Think of the betas as weights. I'm saying, well, how important or how much does it change, holding everything else constant? And I simply add these together to come up with a sum. That sum you have in the past referred to as the y hat. Becomes a predicted value. And then the multiple R squared really is the correlation, it's the squared correlation between the observed value and the predicted value.
I just don't understand the difference then between doing that and the maximum likelihood.
It's just an estimation method. Right? So it's the way that they come up with the weights. It's the manner in which they come up with the weights. In the end, they will come up with the same results, the same weights. The reason I'm talking about the estimation method is because if I introduce maximum likelihood here, when we go to do things like logistic regression, which is next on the list, or after ANOVA, then you've already been introduced to it and you get the concept.
If you have multiple collinearity, are you still stuck with that problem in PGGL?
Well, what can happen with using maximum likelihood is that you can bounce around forever and never find the maximum. Yeah, they keep going, and then in that case, you can have a non-convergence problem. So yes. So yes.
Just like
Right. You still have that look on your face before we jumped away.
I guess I could, you're just saying like the maximum likelihood is a different method of estimating the betas.
That's it.
But you need the maximum likelihood to do other models aside from just OLS.
Right. Right. That's exactly it. Go ahead, hand back to you.
you mentioned something about the difference between general and generalized.
Oh, generalized, right, okay. So the simplest model we wrote down looked like this. Right? That's our univariate model. And then we generalized that to look like this. Right? That is bivariate regression. Right? And then we also, in writing this down, we also made some distributional assumptions about that error term. Right? We said that that error was normally independently distributed with an expected value of 0 and some constant variance, right? And then we generalized that into this equation here. Right, so we go from univariate, bivariate, multivariable, right? Making all the same assumptions about the error term. So this is the general linear model. And then what we can do is we can then relax this assumption, the distributional assumptions of our error term, and make that the generalized linear model. We can say, instead of saying that the error term is normally distributed, if we decide that this error term is logistically distributed, then this becomes a logistic regression. If we decide that this error term is Poisson distributed, which we'll talk about, then this becomes a Poisson regression, and so on and so forth. But in the end, the meaning of these betas don't change substantially. They change in the sense that instead of predicting some continuous outcome that can take any value between negative infinity and positive infinity, we have to think about the nature of our data. I can do bivariate logistic regression, but when I do logistic regression, I'm going to predict what's called a logit. And my logits are going to have some shape, and they can be from negative to positive infinity. But I'm going to make a different distributional shape. Right? And then from a logit, I can then turn those into probabilities, which are meaningful to us, or log odds. And if I do Poisson and so on and so forth, this simply allows me to use the same machinery that we've been using and apply it to data with different scales. Remember we talked about measurement scales? Nominal, ordinal, interval, and ratio. This is where all of these things come together under the generalized linear model. With least squares regression or multiple regression, as we've been talking about it, we're making the assumption that the data are measured on at least the interval scale. Whereas when we generalize the linear model, we can measure things on any one of those scales and still make meaningful inferences. So far so good?
So the general is when you have those constraints on the error term,
Yes.
and generalized is when you don't?
Right. Right. Where we impose different assumptions on the data. Yeah. There's a classic book by McCullough and Nelder. I don't know, it's about 200 or 300 pages, entitled Our Generalized Linear Model, that was published, I think, in the late 80s or early 90s. And it wasn't until then, till these guys from the UK sat down and they thought about it for a second. They said, you know what? Not only is regression and correlation t-test and ANOVA the same, but all these other models are the same too. So the way that I try and teach this is that if you get this, then going to the next, what you would consider to be complicated model, isn't that complicated because you already have a very solid foundation on the basics. Which is why I continually to write down models. This scares a lot of people, but hopefully by now you've seen me write this down enough where it's not as scary, and you can begin to interpret these a little bit better without all the anxiety attached to this. That's it. The thing that would distinguish a logistic regression from a Gaussian regression or a normal regression is the assumptions we make about our error term and the nature of our outcome variable. That's it. Otherwise, it's the same. That's it. It's really not that complicated. Believe me or not, but I think you're having a hard time believing me, but it's not that complicated. Okay. Okay. All right, where were we? Okay, simultaneous regression, and then we included the no multicollinearity, right? So we know what the problems are with collinearity is that we'll get inflated standard errors, and okay, we got that, but we'll get unbiased parameter estimates, okay. And then the third,
While we're back on that subject, can you just say in words again what tolerance is? No, it's the inverse, but then.
Tolerance is really the coefficient of alienation of when I have, say I have k predictors, and I use the other predictors to predict the variable of interest, the predictor of interest, right? So in the case we had here, x1, x2, x3, what'll happen is I can regress x1 on x2 and x3. So what that means is I'll use x2 and x3 to predict x1. From that model, I'll get an r squared, and I'll also get a 1 minus rxy squared. The tolerance is that. That's all it is. And this is the coefficient of alienation. It's the amount of variability in x1 that x2 and x3 do not predict. And if that value is low, then that means the R square is high. That's bad. Yes, ma'am?
So, should we, like, before we put those variables into our model, the explanatory variables, should we be checking for the R square between them?
Well, how would you do that exactly?
Just in the univariate analysis.
Well, we know univariate can be wonky when we go into the multivariate world, right?
Yeah, I think so. I'm trying to.
Yeah, there will be ways of diagnosing this. So I'll show you that.
Okay.
Doing that method of, well, I'm going to look at all the bivariate results,
Yeah.
not a very efficient use of your time. That's what I'm trying to do.
Oh, okay, that's what you're doing, right?
I think we've discussed that before.
Yeah.
Okay.
So you think we should just put them into the model and then kind of let data then assess the multi-variate?
No, you will then, you will diagnose your model. I'm going to teach you how to
Okay.
diagnose your model.
All right, that's fine.
Okay, did I see hands over here? Okay, all right. Okay. Then there's the third approach, which I'm advocating strongly for you guys to think about, is something, well, there's actually a fourth approach, but I won't even talk about it, so I'm just going to write down 4. There's something called set-wise regression. It's also known as hierarchical regression. Okay. Set-wise regression is this approach that we've begun to talk about. We've started to talk about already, where you have grouped your variables into logical sets of variables. For example, in a policy kind of study, you have the concept of demographic variables for which you have no hope or prayer of affecting with your policy, so don't take credit for it. Put those in, and then you might have some other set of variables. And in set-wise regression, you are introducing a variable or sets of variables into the equation in your a priori, well thought out, pre-specified order, where we're looking at the incremental effect of each of these sets of variables. Right. You will also read hierarchical regression. There's also something out there called HLM, hierarchical linear models. Those will also go by the name of mixed models. So if you read something that says that they've used hierarchical regression, you really have to figure out, did they fit a mixed model, or did they use this set-wise approach? Right, so this HLM approach was developed in education, in the field of education, whereas this hierarchical regression, that name has been around for at least 50 years. So this is what we have been talking about. And then there's another approach. I'm not even going to write it down because I don't want to take. I don't want you to say, "Oh, we talked about it in class." There's something called stepwise regression. STEP. Stepwise regression. And stepwise regression. You see how much I like this approach? The stepwise regression. The computer picks what variables you get to include in the regression model. Now, I have a fundamental problem with the computer making decisions for me about my science. So, in a stepwise approach, you can do a forward stepwise regression, or you can do a reverse stepwise regression. In a forward stepwise regression, each variable is entered into the model individually at step 1. And then what happens is that the one variable, or the variable that explains most of the variance relative to the other variables, gets included into the model first. And then it'll take the remaining variables and add them one at a time in the model after you've included that first variable. So in a sense, it's doing this set-wise regression, but it's choosing for you the order in which things are being presented into the model. The problem with stepwise regression is that it plays a lot on chance. Meaning that if you were to get another sample, or even if you were to take another random sample from your sample, it's quite likely that you would get a different set of variables for your final solution. So it's crap. It plays on randomness. It's very difficult to replicate. That doesn't stop people from doing it, but it's a very, very, it has been just shown time and time and time again to be not a good way to do it. So I'm trying to clean up my language here a little bit for the baby. It's that bad that I got sick. I'm overheating now. That's why I'm sick. Trying not to, speak poorly. But it's terrible. Don't do stepwise regression.
Why would anyone do it?
Because that's the way they were taught.
All right.
Remember we talked about retrorectal validity?
But that's cool.
You don't? Well, this is a good, let's take a step back, right? There are 4 kinds of validity that you'll read about in the epistemology of science books. One is statistical conclusion validity. What is that? These are real. The 5th one is we made up, my class and I made up a couple years ago. Statistical conclusion validity addresses the question, what is the degree to which there is a relationship between our variables? Right? So that has to do with correlation. The second type of validity, it has to do with something called internal validity. That's the degree to which the relationships between our variables are indeed causal. The third kind of validity is construct validity, where we can talk about what is it about our treatment and our intervention that caused them to be related. What is it, what is the causal mechanism between the two? And then there's a 4th kind called external validity, which is what is the degree to which I can generalize my results from my sample to other people, populations, and settings, right? A while back, over in the School of Education, we were talking about this in a class, and somebody said, yeah, but I see people using stepwise regression all the time, or change scores. Maybe if we have time, I'll talk about why to never, ever, ever use a change score in an analysis. And people said, well, they do it all the time. And I'll say, well, okay. Well, I think that's a 5th kind of validity. We call that retrorectal validity, right? And that means something is valid because some people has done it in the past, right? And tradition, or just because somebody has done something some way in the past, I would argue is probably the most unscientific reason to do something, because then that borders on religion and not questioning why something has been done.
Can you just briefly explain setwise again? I just want to make sure I have
So
it.
it's what we talked about, or what we've been talking about. Let's say, for example, let's come up with a set of variables. What are you interested in studying? So what was your name?
Ilona.
Ilona?
Yeah.
Let's help you design your study, Ilona. What are you interested in studying?
Knowledge of diabetes.
Okay, so diabetes knowledge. And what do you think could predict or could affect level of diabetes knowledge? Everybody can chime in here, we'll participate. What can affect this?
Education level.
Okay, so education level, what else? Just call them out. Age, what else?
Family members, diabetes.
Family history, maybe? Okay, what else?
How many years you've had? Yeah, like the
Years with disease, what else?
Insurance.
Insurance, insurance people. What
Income.
else? Huh? Income. What else? Primary language. I heard something else, but I didn't.
Quality of their doctors.
Quality of treatment. What else? Anything else? All right, well, we'll stop here. But you're going to have some intervention, I assume, too, that you think will increase, level of diabetes knowledge. What is that intervention? Should we just call it intervention?
Sure.
Let's call it intervention.
So this is where we just divided our variables into things that we could impact. Okay.
Yeah.
All right. I just want to make sure that I have it right.
Yeah. So then in that case, what I would encourage you to do is maybe first do your demography.
Right. Okay.
And then maybe those medical care things, and then finally your intervention. Okay, all right. Oh, son of a gun. Okay, so with multiple regression, we've now introduced 3 new assumptions that are associated with it above and beyond the assumptions that we included for bivariate regression. Does anybody remember what those things are? No multicollinearity. What does that mean in English?
That your predictor variables are independent.
Yeah, statistically independent. Okay. And there were 2 more that we talked about last week.
Unbiased estimate.
Hmm?
Unbiased estimate.
Yeah, it leads to unbiased estimates. What's the assumption that allows us to have unbiased? The what? No, that's an assumption that goes back to bivariate, right? The homoscedasticity, equal variance. Right? Remember when we looked at the relationship between age and memory span, ignoring speech rate, and the interpretation of the relationship between age and memory span was, oh, it's positive and strong. But then when we partialed out the effect of memory, what happened to the relationship between age and speech and memory rate? It flipped and went down to essentially 0, right? So the other assumption that goes into multiple regression is that we've included all relevant variables. It's an assumption. I know last week I think Andy was talking about propensity scores. Did he talk about the ignorable assumption? That word ignorable, that didn't make any sense? Okay, never mind. Well, we'll talk about that a little bit. Right, so that has to do with so you've included all relevant variables in your model, because we now know that if we exclude an important variable, we know that any one of those variable signs could flip, the magnitude can shrink, right? And then the third assumption that we talked about was we have properly specified the functional form of the relationship between the variables. So that means not only did we include the proper variables in the equation, but we have also put them in, we've expressed the proper relationship. Meaning, if age belongs in the relationship, let's say that the real relationship was age squared, and age cubed. Right? So then we have this funky looking curve going on. Because even though we say linear regression, that doesn't mean straight line. It means linear in the sense that we're adding components together up there, right? The functional form says that we have properly specified the relationship between the variables. So maybe the relationship is age and age squared, age squared, age cubed, and so on and so forth. That's another assumption. Because if we misspecify our model, the degree to which we misspecify our model can yield to highly biased estimates. And yes, it's an assumption. Will we ever know we're right? No. But we call it a simplifying assumption. Okay? I'm about done. I'm actually swimming in my shirt here, so it's sweat, so I apologize. So what I want, I'm sorry. I do. I'm going to post something out on Blackboard that it's going to be entitled NHST, Null Hypothesis Statistical Testing. And I want to talk about the relationship between causality and experimental design, what p-values are, and things like that. Because I think before we get into modeling multiple regression, let's refresh what those things are, what a p-value is, what a p-value is not, the whole idea of how your study design should inform, your question should inform your study design then informs the way you analyze your data, and then all of those things go into how you interpret your data. Right? And then the next week, then really we'll spend about a week on
multiple regression. It's not that hard, honestly. It's really not that hard. And then we'll do ANOVA after that. And then we'll go into more fun stuff like logistic regression, okay? Good. Any questions before we break? We're good? Okay. So if you guys are interested in looking forward in the book, look for things like leverage statistics, influence statistics, something called Cook's D, variance inflation factor, tolerance, those sorts of things. They're going to be in the textbook. The previous cohort had good feedback for that stuff in that book.